Today, I'm going to take a critical look at Ampere's law. I'm going to run a current through a wire, as we did before, but now I'm going to also put a capacitor in that line, and so we are charging a capacitor. Here's that capacitor. Here's the wire. We're running a current I. And as we're running this current, clearly, we get a changing electric field inside the capacitor. The electric field inside the capacitor, sigma free divided by kappa epsilon 0, which is also Q free divided by the area. This is a circular plate capacitor. Capital R is the radius of that capacitor. So we get pi r squared kappa epsilon 0. But since I run a current, the Q free is building up all the time. And so the current, per definition, is dq dt. And so I now have a changing electric field inside the edt, which is the current I divided by pi r squared kappa epsilon 0. Because I simply take the derivative of this equation, I get dq dt, and dq dt is I. And only if the current is 0 is there no changing electric field inside. So how does this affect the magnetic field? Well, if I take here a point P1 at a distance little r from the wire, if you're far away from this capacitor, it's hard to believe that Ampere's law would not give the right answer. And we'll apply that very shortly, Ampere's law. It's on the blackboard there. Suppose you are at the same distance from this line here at point P2. Well, yeah, you've got to admit there is an interruption of current now. There is no current going through this space. And so you expect that the magnetic field here would be a little lower, perhaps, than it is here. But not very much. So the question is, how can we now calculate the magnetic field here and there, now that we have this opening in the wire? Well, Biot-Savart could handle it, but I wouldn't know how to do it, because if there's a current flowing like this, there is also a current going up on these plates, and one like so. And I wouldn't know how to apply Biot-Savart. In principle, yeah, but in practice, no. How about Ampere's law? Well, let's give Ampere's law a shot. This is a cylindrical symmetric problem. So I choose a closed loop, which of course itself is a circle with radius r. And I attach to this closed loop an open surface, that's mandatory. And I give myself an easy time, I make it a flat surface. So now I apply Ampere's law. You see it there on the blackboard. Anywhere on that closed loop, the magnetic field will have the same strength for reasons of symmetry. And so we get B times 2 pi r equals mu 0 times I pen. And pen means the current that penetrates my open surface. Well, that's I. I goes right through that surface. And so the magnetic field at that point P1, mu 0 times I divided by 2 pi r. We've seen this several times before. Now I wonder about P2. Can I apply Ampere's law for point P2? Well, yeah, you can try. So now I attach a closed loop to this point. Circle, again, radius little r. And I use this flat surface, and I apply Ampere's law. well, I'm in for a shock. Because B times 2 pi r is not changing, but there is no current that penetrates that surface. And so I is 0, and so I have to conclude that the magnetic field at point P2 is 0, which is absurd. Couldn't be. I can make the situation even worse. I'm going to revisit point P1, and here is my capacitor, and here is my point P1. My current is flowing like so. Here's my closed loop, according to Ampere's law, closed loop integral B dot dl. Why should I choose a flat surface? I'm entitled to any surface. I like surfaces like this. They are attached to a closed loop. So I will choose that kind of a surface. The surface now goes like so. Right through the capacitor plates. And I apply Ampere's law. So it's open here. B times 2 pi r. This radius is little r. Mu 0 times I, but there is no I going through that surface. Nowhere through this surface is a current poking, because there is no current going between the capacitor plates. So now I have to conclude that the magnetic field at P1, which we first concluded was this, is now also 0. So something stinks. So Ampere's law is inadequate. And so, of course, Faraday and Ampere were both perfectly aware of this. But yet it was Maxwell who zeroed in on this, and he argued that any open surface that you attach to a closed loop should give you exactly the same result, the same answer. And so he suggested that we amend Ampere's law. And so he asked himself the question, what is so special about in between the capacitor plates? Well, what is special there, that in between the capacitor plates there is a changing electric field. And Maxwell reasoned, gee, Faraday's law tells me that a changing magnetic flux gives rise to an electric field. So he says maybe a changing electric flux gives rise to a magnetic field. And I want to remind you what an electric flux is. Phi of E is the integral. In this case, it would be an open surface of E dot dA. That is an electric flux. With Gauss' law that you see on the blackboard there, we had a closed surface. I'm talking now about an open surface. That is an open surface. This is an open surface. And this is an open surface. And so Maxwell suggested that we have to add a term which contains the derivative of the electric flux. And that's what I'm going to do there now, walking over to Ampere's law. I'm going to amend it in a way that Maxwell suggested. He adds a term here, epsilon 0 kappa, ddt of the integral over an open surface attached to that closed loop of E dot dA. This current, which is the one that penetrates, remember, through the surface, is really a real current. This term here, Maxwell called displacement current. I want to make sure that I have no slip of the pen, because I hate slips of the pen. That is correct. I have everything in place. You may think now that we can start a party because all four Maxwell's equations are now in place. Not quite. We're going to make one small adjustment after spring break. And that adjustment is going to be made in this one. And then we'll have our party. So now, I would like to use the new law and see whether we can clean up that mess. So I'm going to revisit my point P1, and I'm going to apply the new law by first having a flat surface, that surface that we have here, and then trying this surface. And I want to get the same answer. If I use that surface, do we agree that there is a current going through that surface, but there is no electric flux going through that surface? So that second term, that displacement current term, is 0 for that flat surface. So this answer is completely valid. But now, I want to pursue this case. And so I make a new drawing. We have here this point, P1. This is my radius, little r. This is my surface going right through here. Here's the current, I. And here's my changing electric field. And so I get B times 2 pi r, mu 0. I pen is 0. There is no current penetrating through this bag. This is open here. So the first part is 0. So I only deal with the second part, which is epsilon 0 k, kappa, displacement current. And now I have to put in there d phi e dt. Phi e is very easy to calculate because E and dA, right here, think of this part being flat. Wherever you are inside the capacitor, if we assume that there are no fringe fields, then there is an electric field only when you're inside the capacitor, and so the electric flux is simply E times the surface area. E and dA are in the same direction. So it is the electric field times this pi capital R squared. And therefore, if I want to know what the derivative is, then I get this pi R squared, which is that surface area, and now I need there dE dt. And the dE dt we have, that is I divided by pi R squared kappa epsilon 0. I divided by pi R squared kappa epsilon 0. So this is the area A, and this is the EDT, and this is the area of the part inside the capacitor that has a flux going through it. Because outside here, there is no flux going through there. So there's no contribution. There's no contribution here either. There's no contribution here either. The electric field is only existent there. That's my assumption. And so the whole thing here is now d phi e dt. Well, let's look at our results. I lose a pi. I lose my r squared. I lose my kappa and epsilon 0. And look what I get. I get mu 0 times I. That is truly amazing. So I find now that B equals mu 0 times I divided by 2 pi little r, which is exactly what we had before. Hooray for Mr. Maxwell. Because now it doesn't matter anymore whether you take the flat surface or whether you take the bagged surface. You now get the same answer. In one case, there is no contribution from the displacement current term, and in the other case, there is no contribution from the first term, the real current. Let me make sure whether I'm happy with my results. Yeah, I think that's fine. We can now also go one step further, and we can calculate anywhere in between the capacitor what the magnetic field is. I'll make another drawing of the capacitor. It's right here. I have this E field. I will not repeat that every time. And here I have my point P2 now, which is inside the capacitor at a radius little r from the center. And this is capital R, circular plate. I have here my closed loop. It's a circle. It's radius little r. I apply now the new law. B times 2 pi r. And there we go. We have a mu 0, we have an epsilon 0, we have a kappa. There's no current going through here, so it's non-negotiable. I pen is 0, right? That's not even an issue. So we get mu 0, epsilon 0, I get kappa. But now the surface area right here is not pi capital R squared, where there is a changing electric field, but it is only pi little r squared. I take a flat surface now. And so now we multiply this by pi little r squared, and then of course dE dt is the same. So we get our current I divided by pi capital R squared divided by kappa epsilon 0. And now you're again losing a lot. You lose your epsilon 0, you lose your kappa, I lose a pi. And look, I have a little r here and I have a little r square there. So now we're going to get a result, which is something that you may actually have anticipated, namely that you get a field inside the capacitor that is growing with r. Because if I make up my balance, I get upstairs mu 0 times I, but I get one little r upstairs. You see, you have r square here and you have r here. And downstairs, I get 2 pi, and then I get a capital R squared. And I believe that's correct. Let me check my notes. And yes, I'm happy with that. And this is proportional with little r. Whereas here, falling off 1 over r. And so I can now make a plot of the magnetic field as a function of little r when I'm inside the capacitor plates. Little r, this is the magnetic field, and this is the radius of the capacitor plate. It's going to be a straight line up to that point, and then it will fall off as 1 over little r. And you can do your homework on that. That is very trivial to calculate, to demonstrate that when you go beyond the edge of the capacitor, that then it falls off as 1 over r. Just in the same way that point P1 is doing. So now we have a tool to calculate the magnetic field even inside capacitors while we were charging, which we didn't have before. The strength here, the maximum magnetic field here, you find by substituting in there for little r, capital R. And when you do that, if this becomes capital R, this becomes 1 over capital R. If you had substituted in here for little r, capital R, you would have found the same result. This part is not kosher and cannot be correct. And I cannot make it right for you. And the reason why that part cannot be kosher is because we have made the assumption, which is wrong, that there is no fringe field. And so we have assumed in our calculations that the electric field is only here and there, but it's 0 here, so that there is nothing, no dE dt here, no changing magnetic electric flux. And that's not true. So clearly, when you get close to the edge, this is not correct. And there's no way I can correct for that because the fringe fields will be different from capacitor to capacitor. And those calculations, of course, are not even very easy to make. When Maxwell had introduced his displacement current term, he was a very smart man. He predicted that as a consequence of that term, that radio waves should exist. There was a time that we didn't know that radio waves existed. He predicted their existence. But not only did he predict their existence, he even was able to calculate what their speed was going to be. We call that the speed of light. And we will do that in a few weeks ourselves in 802. In 1879, which was the year that Maxwell died, the German physicist Helmholtz asked one of his students, Hertz, he was 22 years at the time, he was a junior, to try to demonstrate that radio waves indeed exist. Hertz declined because he argued that the equipment that was available at the time was not good enough. But 7 years later, when new equipment had been developed, he accepted the challenge. And it took him 2 years, but then he indeed was able to demonstrate that radio waves do exist. Imagine what a victory that was. Someone like Maxwell, who predicts out of nothing that radio waves should exist. And here comes someone who actually shows that they do exist. Hertz died 5 years after his great experiments. He was 37 years old. He was very young. Had he lived 10 more years, there is no doubt in my mind that he would have been awarded with the Nobel Prize for Physics. But the first Nobel Prize was only given in 1901. So he died just a little bit too early. Maxwell also died very young, age 48. Why did Maxwell call that strange term displacement current? In the presence of a dielectric, if you put a dielectric in there, a changing electric field will indeed cause a current in between the plates, because the polarization will change all the time. You get a rearrangement of these induced charges. So there is indeed a current. But in vacuum, there shouldn't be any current. Any electric field changing or not changing will not cause a current in vacuum. But Maxwell believed that vacuum in a way behaves like any other dielectric, just a special dielectric. Happened to be a dielectric with kappa equals 1. And so he really believed that there was an actual current going between the plates, even though we now know, of course, that that is not the case. So the name displacement current was perhaps not a very lucky one, but the term is a must. And it completes the theory of electricity and magnetism. The name is obviously of no consequence. After all, Shakespeare said it himself in Romeo and Juliet, what's in a name? Remember, what's in a name? That which we call a rose by any other name would smell as sweet. Those were the words by Shakespeare. I will abandon for now the displacement current, but we will revisit it later when we will deal with radio waves and with the propagation of electromagnetic radiation.